So I'm here presenting quite a large group. It became over the years with a very diversified background between industry and academia. So just to say the name very quickly, I'm with Theodore, Mark, Linus, Joao, Reza, Carl, and Gianluca. With us, there are also 5 professors, so Matteo, Sein, Hedvig, Daniel, and Jussi. We've also been supported by several major institutions over the year, both from industry and academia. And our work that I'm going to present, and also the one that we're working now, has been published over the last years in ICCV and DCCV. So why supercomputing in our case? So this is an application where we are using Leonardo supercomputer, handled by Cineca in Bologna, for an application which is quite far from supercomputers, which is AI on the edge. So for us, when AI on the edge, now everything, like the thing that comes to our mind the most is indeed autonomous driving. But it's not just about autonomous driving. Recently, we see a lot of interesting development with humanoid robots and other applications. And of course, here we have the opposite problem of supercomputer. The data is not there. There are no annotation. The compute is super limited. So we have to think about, in a different paradigm, how to use AI in this context. So I've worked in autonomous driving for quite some years. And I can safely say that we have reached a state of superhuman perception. We have a vast array of sensors in our system, and we can really detect better than humans in so many fields, which are such a higher precision. Therefore, autonomous driving must be a solved problem, right? Well, it's not like this, because it's a solved problem until the unexpected happens. And the problem is the unexpected happens all the time. Just a very quick and simple example to show this is that here I'm showing 2 images. This is the task called semantic segmentation that has been mentioned in the previous presentation, and it consists of basically giving a semantic meaning to each single pixel in an image. And we can see that this is a proxy task that can be done in academia, but also in industry, and it's really useful because you can really understand what the car is seeing. But then you see that this is a state of art, and then you just add a couple of droplets of rain in the image, and everything falls apart. This is in the field is called domain shift. When you approach a domain which is different from the one that the network has been trained on, then everything fails. So how do we solve this? There are many answers. I'm going to go over 3 correct answers. The first one is what everyone is thinking about. So just add more data. Well, it's true. Data is the base, as we said already, of AI, but it's not just that. First of all, add more data is very slow. It's also very expensive, especially if you want to annotate this data, and you want to annotate this data with an ethical workforce. But it's not just that. We have a problem of long tail. So the data that you collect more easily are data that probably you already have, and then not very useful. We have a problem, of course, of dimensionality, because domains combine on each other. And we have data obsolescence. You think that the data is forever, but actually, even if you don't want it and you don't know, every data point that you have has an expiration date on it, because the sensor changes, task change, everything changes. Another correct answer could be, well, why don't we generalize? So let's just have some augmentation in our data. Try to break some biases here and there. That will fix the problem. Well, not really. We all do it, but it's not really fixing the problem, unfortunately. And sometimes we even break biases that we don't want to break, so we cannot even go crazy with augmentation. And on a more philosophical stand, can we even prepare for the unknown in some sense? Like there are some unknown unknowns that we really cannot even augment. So then there is a third answer, which is a bit unexpected. And how are humans solving this? So we don't really are so much reliant on data, and we don't even augment our data, really, but we adapt. So what does this mean? In AI, there is a field called unsupervised domain adaptation. So this is a field that came, let's say, to the success thanks to simulation environments. Because simulation environments, we talked about synthetic data recently, they provide a lot of data perfect in terms of annotation, because the annotation comes with it, and it's accurate. The problem is they're different from the real data. And when you take this model, as we've seen before, and you train on synthetic data, you deploy them in the real data, in the real world, and then they fall apart. So then we need a way to adapt this model to real data. But most of the time, we don't have the label of the real data. Also, that's the most expensive and complicated part to do. So domain annotation tackles this problem. How do we do this transition? And there are several methods that can do it. But still, there is something missing. That even if we can do this transition initially, once you deploy the model cannot be frozen, because domain happens all the time. Domains change unpredictably. And not only unpredictably, it can also happen very fast. So we had a seminal publication when it came to that, and it was in 2022, and it's called Online Domain Adaptation for Semantic Segmentation in Ever-Changing Conditions. So effectively, tackling domain that changes continuously, and making a network that is able to tackle these changes without any human intervention. Then this publication in 2023 followed, and called To Adapt or Not to Adapt, Real-Time Adaptation for Semantic Segmentation. And this tackled the problem of doing what we were already doing, but doing it in a timely fashion, because when you have an autonomous driving car, you cannot afford to wait 5 minutes for the car to adapt to a new domain. You need that to happen very quickly. Of course, we can see that our method, that is called Hamlet, beat the state of art. It's both very fast and very accurate. And of course, I have a video actually here to see. You can have an idea of how this looks. So you see state of art of semantic segmentation on the left, and it's pretty poor. You can see this is a YouTube video, so nothing that the model has ever seen before. And a non-adapted model is really poor, can really say what's happening. In the Hamlet model, we can see that most of it's correct. And all of this the model is adapting online. So as the images are coming to the model, then the model is just learning how to handle them. So of course, this is something useful for, let's see if I can go to the next slide. Okay. So of course, companies are naturally already interested about this. So which company would ever try to do something like this? So I don't know if you've read this article. It came out late last year, and we actually didn't know about this. So OpenAI agreed to buy $51 million of an AI chip from a startup backed by CEO Sam Altman. And then if we read a bit here, we see okay, this company called Rain AI is developing something brain-inspired. So what is it about? So Rain AI, the startup, said, focusing the computation on something called neuromorphic computing, which is something that brings the training of AI model within the storage of the model itself. But even if you do the training on the model, then you need something to train on. You need an algorithm that can train online without any human supervision. And therefore, to do the on-device fine-tuning, they rely on us. They rely on Hamlet. There is a catch. So is online adaptation safe? And the answer is no. Or better, not yet. So why? Why is it not safe? Because this AI to train by itself, of course, it needs some supervision. And the supervision is given by another AI, usually an older instance of the AI itself. And this could create a dangerous loop, because you can learn from past mistakes, not knowing that they are mistakes. So we need two things, control and explainability. We need AI that we need to control what the AI is ingesting. And you also need some form of explainability for us to rely on it, especially for safety-critical applications such as autonomous driving. And that's basically the research that we are now doing in Leonardo. So we can imagine that most of the cases, like in industry, but also in academia, you have not one big data set, but you have a lot of buckets with data. And each bucket can effectively represent a domain. So here we see one bucket with clear images, one bucket with some rainy images, snow and night. We can theoretically fine-tune a model on each single bucket. So we will have a lot of models. And we can have a lot of models because we have a lot of data now around. And the good part is that maybe you can even create some form of marketplace of these models without giving access to the bucket of data that these models have been trained on, such as a marketplace. But this doesn't really solve the problem, because let's say that we have a domain that is quite similar to the night domain, or I have maybe a domain that has never been seen before, like fog. We don't have it in this example, so how does the AI know that has to pick that specific book, that specific fine-tuned model? So this doesn't solve the problem by itself. So what we need to do, if you have a bunch of books and you need to find one, is to create a library, an indexing system. So to do this, we rely on CLIP, which is a model released by OpenAI in 2021, which can reproject both images and text in a unique space, in the same space where similar concepts lie close to each other. So then each single bucket can go in this space. And then what do? We have the index, and now we put the models indexed in this way. And now we have one domain. Oh, we have a domain that is similar, and then we just pick it. Effectively, we give a compass to the AI. But this doesn't really solve the problem, because let's say that we have a domain, and unfortunately, we don't have any domain with fog here. So what do? Well, the answer is that if you go in a library and you're looking for a book, but this book doesn't really exist, it doesn't mean that the knowledge that you're looking for doesn't exist in the library. It could just be spread over other books. So what you do is usually to start searching and learning and studying. So the answer is we take the remaining parts of the library, and based on the distance that they have in the CLIP space, we generate a new model by fusing the existing fine-tuned model. We fuse them together, and then we deploy this model in production effectively. And this takes really zero time, because there is no training involved in everything that I'm talking about. So let's see the system just all together. We have an RGB stream from images, let's say autonomous driving. And then we have something called domain observer, which is CLIP, effectively projecting images into the space. Then what we do is that we project this point, the current domain where we are in CLIP, fetch the fine-tuned model that we care, fuse them, and then take this fused model and put it in deployment. And this is really controllable, because we can even measure the contribution of each single model in the deployed one. So for example, here we have rainy images, and then we can see that this yellow part here is the most important one. Why? Because this is indeed the model fine-tuned on rain. But we also see that the other models are still contributing to it and effectively making it better. So here we go to, then in the sequence continues with foggy images. And here we see that fogs take the priority. And then we go here with snow, and then clearly the purple one that represents the snow book is the one that is the most relevant for this new fused model. And finally night, that unsurprisingly also the night data are taking the lead. So why supercomputing in this? Well, the thing is, like, there are many models, many buckets of data. So our goal now is to take this approach that I've just shown you, that is just with 4 buckets, and expand it to effectively, like, could be hundreds or thousands of data sets, and fine-tune all of them, and then merging according to this method. So thank you all. This was my presentation.